capture deep sky objects. So that's short introduction about me, and I'm going to share some presentation, but it's going to be in Lithuanian, so sorry about that. I don't have prepared the English one. Okay, so I'm not sure if you can see it already.
Yes, we can see it. Everything is okay.
Okay, cool. So this will be structured in such a way that I'll talk about the theoretical part of astrophotography for a little bit, but not too long. And then I'll switch off the presentation and just display how the gear is assembled and how and what kind of software I use to do the imaging, and then a short overview over image processing. So how does the captured images become the final product? So what is astrophotography? Astrophotography is well, not art, but a way of capturing sky and then various events that occur in sky, and usually associated with deeper objects not in our atmosphere. So meteors, our Milky Way, galaxies, etc. This hobby became popular back when digital cameras became available to consumers. So amateurs became able to purchase and use cheap hardware to capture the sky. And it was especially popular, became especially popular with digital cameras, because before you could use film, but with film it was quite a lengthy process to do everything, and the end result was usually subpar. Considering that digital cameras is not the only thing that's necessary to capture, another kicker for amateurs was cheap hardware, such as mounts and telescopes made in China, because their quality usually is a bit lower. So and it's manufactured in big quantities, so it's cheap, and amateurs love the hardware that's cheap, because they can get into it, even though they're not that accurate and have some issues. But we amateurs like to tinker with our hardware and find ways how to overcome their cons. The actual astrophotography consists of two parts: the actual photography and image processing. These two parts are inseparable from each other in this hobby, because it's the photography of deep sky and is a low light photography. So you capture very little amount of photons. All the images are very dark. So you have to process the image to extract the hidden image in the darkness. You'll see what I mean when we'll get to the image processing part. And it has like these couple of types astrophotography. It's wide field astrophotography. It's usually Milky Way, maybe it consists with other objects like trees or some other beautiful scenery, but it's usually of a wide shot of the sky. Then there is deep sky astrophotography, when you're imaging galaxies, nebula, star clusters. This is the one that I'm doing and I love the most. And then there's planetary or lunar photography. It's not the same as the other two because usually you're not actually photographing, but you're making a video. Well, it's kind of the same thing, but just a lot of photos. So the reason behind that is because atmosphere is unstable and the planets usually wobble in the frame, and you have to capture lots of frames where atmosphere is stable and the image is sharp. So we have to do like a couple of thousands of images so that few hundred of them would be usable. So they would be sharp and not smeared across the screen. Yep. Next part is about what do you need for deep sky astrophotography. So there are two parts of this. It's mandatory equipment and additional or optional equipment. So the first thing is Equatorial Mount. I have one. I'll show you what it is. Basically, what it does is compensates rotation of Earth. So if you were to take image of the sky with a long period of, well, with a long exposure, you'd see that stars are starting to go across the frame. So instead of a dot, you'd see a line. So you need to and this is the result because of Earth's rotation. Earth is rotating, and the camera is stationary, and the star is just going across the sensor. So you need to compensate for that, and Equatorial Mount is what you use to do that. It's just rotating at the same speed as the Earth is around this axis. So 360 degrees around, it would take 24 hours. Well, next thing is optics. So either telescope or what's this word? Telephoto lens. You'd want to usually from 100 and upwards of millimeters of focal length, at least. And then, of course, a camera. It can be either DSLR or mirrorless or just some other specialized camera that you use. I use a specialized camera. And then you need a power source. So you could be able to power the Equatorial Mount and maybe optionally a camera. From the optional gear, you need you could use, you don't need, you could use a filter wheel with filters. So this accessory is used when you're using a monochromatic camera, which captures only images in black and white. And in usual DSLR camera or your phone camera, you have already filters built into the camera itself. So these the sensor is made up of lots of pixels, and each of them is covered with a little dot, which allows certain light to pass through it. For example, one pixel is always capturing only red light, the other green, and the other blue. So with my camera, I can capture only certain light for the whole sensor. So I'm using red filter to capture red photons, green for green, blue for blue. And then I have joined 3 images into one, make it appear in color. Another thing is guiding camera. This accessory is necessary to compensate for inaccuracy of cheap Equatorial Mount. So my Equatorial Mount is compensating rotation of Earth, but it's not compensating ideally. So it either sometimes moves faster or moves slower. This results in stars appearing like blobs or lines, not that big lines, but smaller lines in the image. And the guide camera, what it does, it's a separate camera using a usually separate optics, which is monitoring one specific star in the field of view. And if it detects that star moved from one pixel to the other, it means that the mount is making an error. So the software that's monitoring that star issues a command to Equatorial Mount to move slower, so that the star would move back inside that pixel that it's supposed to be. Yeah, and then you need a PC for more complex cameras, because it's not a standalone camera, like in my case. Yeah, so that's theory done. Won't bother with that too much anymore, only when assembling the gear. And I'm going to stop the presentation now. Okay, you can see me?
Yes, we can see you. Thank you.
Okay, so starting with the gear, you need a tripod. It's a big one because you need one that it can handle a lot of weight. Then comes the Equatorial Mount. It's a big one. It can handle about 25 kilograms of equipment. So we assemble it onto the tripod. And I'm not sure if you can see the mount itself. Yeah, this should be better. Yeah. So what it does, it moves in 2 axes, but it can move in 2 axes. But when taking a picture, it's moving in 1 axis. So you have to put it in such a way that looking through here, it would point to the northern star, the Polaris. And then it just only rotates on this axis, the same one that our Earth is rotating, and this compensating its rotation, so that the stars will remain in place, and etc. Now, as the telescope will be put onto one side, we need to put counterweights on the other side, so that it would not flip over and crash, because that would be expensive. This little thing, screw, is called a nail safer, or I'm not sure for exact translation from Lithuanian, but its purpose is to make your toes and nails safe, because I'm putting these counterweights onto the shaft of the counterweight bar, and they potentially can slide off. So to avoid the damage to your toes and nails, this thing screws on and prevents counterweights from sliding down. I'm putting on 15 kilograms of counterweights, and they can be adjusted on the shaft, how far they go, so we could balance the forces out, and the mount would be in equilibrium of forces from both sides. So that the electric these motors would not be strained, and they could push around the mount easily, and would not burn. Now, I'm putting on this telescope. This is 25 centimeter Newtonian telescope. So what that means? Well, it means that it has a mirror of 25 centimeters in diameter back here. And it has a smaller mirror here, which is angled at 45 degrees, like this, so that the light, when it's falling into the telescope through this end, would bounce off the main mirror into the secondary mirror, which is at the angle, and then the light would bounce off from it into the sensor of the camera. This design dates back a couple of 100 years and is cheap and easy to make. It also provides good cost for big aperture, and big aperture allows us to capture sharper images and objects that are further away in the universe. Right, so what I mean by finding equilibrium of forces is this. I'm moving the counterweights here, and then I can rotate the telescope without much force, just using one finger, and that's it. So this means that electric motors inside the mount won't have to struggle to move it. So, okay, next thing, what can we see in here? I'm not sure how much resolution does the camera provide, but basically on this side here we have a camera. It's a little black cylindrical thing. Then the filter wheel with 5 filters. I have RGB ones and some narrowband filters that allow certain light to pass through. For example, light that is emitted by doubly ionized oxygen. It provides a different insight into the composition of objects and allows to image objects differently. And it also allows me to image from heavily light polluted skies because it cuts out on the very precise part of the spectrum, so that the other lights that create the light pollution, for example, street lights, are not inside that spectrum. So these filters allow me to capture the target, and they are not affected by street lights or in general light pollution which is in the city. Yeah, and then I have focuser here. So if you're familiar with a lens on a camera, you usually rotate the string, and it moves optical elements inside it further or closer together to reach focus in certain distance. So this, in principle, this thing works the same. It just moves this whole assembly outside or inside, so we could reach focus in infinity, basically. And why so many wires here? Well, because everything's automated, and I control everything with a computer. So focusing, filter changing, image capturing, mount movement, everything is done with a computer and is automated. If I had permanent place to put my gear, for example, observatory, which might happen quite soon, I would not have to do all this preparation that I did here. I would only have to turn on my PC, find the target that I want to image, and tell software to start capturing the frames. Now, how does that look like? I have my computer here, the imaging computer right on the telescope. So I just only need to connect it, and I'll show you quickly the process of starting a capture. So before that, I'll just talk quickly about how I select target and how I can image the same part of the sky a couple of nights in a row. So there are quite many different ways how to figure out what you want to image at a certain night. There are also some limiting factors. For example, some objects do not rise at certain period of year. In general, spring is considered galaxy season, as the part of the Milky Way that contains various nebulae does not rise. It's hidden behind the sun. So you have to take that into consideration when selecting a target. And then there are multiple maps of targets. There are people who already imaged majority of the targets. So you go and into these maps of various targets, or just look at pictures that other people already took. Well, then on your personal preferences, you select what to image. Maybe it's a popular target, but it's very interesting, beautiful, and you just want to image that because it's nice. Maybe it's a target that's very obscure, very rarely imaged, and you want a challenge of capturing a rare target that not many people are imaging, so that you could do a better job than them. It's usually not that easy to do a better job than other people, because there are in the whole world there are thousands of astrophotographers. So yeah. Right. So I'm going to share my screen once again, and I'm going to share how the software part looks like. So it's the second part of the demo. All right. So you should see the screen. Right. So yeah, I connect my imaging computer via some remote desktop client. In this case, I use AnyDesk. And here you can see the main software for what I use for image capturing. It's called Sequence Generator Pro. And what it allows me to do is add a list of targets, enter coordinates for those targets, because whole sky has coordinates, just same way as our maps for finding, for example, you want to find how to get to Kaunas, so you or Vilnius, you know the target of specific location, you have coordinates. Same goes for sky. It's just a little bit different. So these two numbers are coordinates in the sky. Then I just select when to start imaging and when to end. Pick my frames that I want to capture. For example, I want to capture red photons for 90 seconds per frame and total of 75 frames. The same goes for blue, for green and blue. So in the end, I would have like 260 frames. Oh, I'm sorry. I'd have 225 frames and colored image after I process it. Capturing all those frames would take a little bit more than 5.5 hours. So after I enter all these parameters, I connect the gear, and then I can just click on Run Sequence, and off we go. The other software is PhD2. So this software is designed to track that star that I talked about earlier. So it would stay in the same place. Should connect a little bit. Okay, as software is not cooperating with me, I'll show it on simulation. Okay, so yeah. We start the capture of imaginable sky of simulation, and we can see multiple of stars. So if we select one star, it starts tracking that star. We click that we want to adjust our mount movements. It does a calibration beforehand, so it would know that when moving upwards means moving one axis on the mount, moving to the right moves different axis. Basically, so it would know which side is up and which side is down. Let's imagine it already knows that. If we just start guiding, and here in the corner we see that the star is hopping around. So it means that it's not moving ideally. And in this graph we see what kind of adjustments the software is making for the mount. Okay. Yeah, one more thing with the coordinates of the target. So one thing is to enter the coordinates, the other is to find where in the sky the telescope is pointing to. So initially, the telescope and the software do not know where it's pointing at, but we know where we want to be pointing at. So what do? We take an image of the sky we're currently pointing at, and we run it through the software that matches that area of the sky with the stars to a dictionary, an atlas of stars, and it can find the way that stars are placed inside the image, how they are referenced towards that atlas, towards the dictionary. So it runs through the algorithm, figures out the coordinates of that image that you just captured, and it knows then how far off from the target you are, and then just gives commands to mount to move to those coordinates you wanted to initially. Okay, so with the capturing, it's pretty much it. To get to this point, actually, it takes quite a bit of trying and failing and seeing how everything works. But in the end, it boils down to knowing what kind of errors mean what, and then just adjusting to that. And when you know how everything's set up, you just come in, click run, and that's it. And then you can go to sleep. All right. So last part of this presentation is image processing. You can see this program, right? Okay. So how does the image look like when you take it out of the camera for after just capturing part of the sky? Like this. So this image is a single frame of galaxy of 5 minutes, and it has various artifacts. So after removing artifacts with certain routines, you receive image that looks much better. So before and after. Then you run this routine through all the images that you capture, and then you combine all those images together into one. And the end result is this. So this image is a single frame. This is when you combine 100 or so images together. So the difference is quite striking. How does that happen? Well, when you combine multiple frames, in one frame you have a photon hitting certain pixels, in the other maybe not, because it's not a continuous stream of light, but it's individual photons coming from that galaxy far, far away. So if some frames missed some photons, some did not, you in the end combine and increase the knowledge of whether that pixel should contain data or not. And that difference is called signal to noise ratio. So if we remove the photons that are that should not be there, and we add together the photons where we know that they're we know that they're supposed to be and they truly exist, because they show themselves in multiple of images. So this is a luminance frame, so it's used for details. And then we have the frames that are used for to combine into color. So this whole frame is consists only from blue photons, this one from green ones, this one from red ones, and then I have even the narrow band image that consists of photons that are created only by hydrogen alpha. So the atoms of hydrogen emit light, and it's emitted in two parts of spectrum, alpha and beta parts. And I specifically image alpha part here. So difference is very, very striking. So red compared to hydrogen. All this, these stars and the galaxy itself, where it's shining, it's all hydrogen. Compared to red, which is generated by other elements as well. Now, we want to combine red, green, and blue into colored image. And when we combine, it becomes this. We already see that it has some color, but it's weird. The color does not look natural. And the reason behind that is because camera captures photons of different color differently. So for example, it's more sensitive to red color rather than green. So it will have a higher intensity red image than green. And this is only just down to purely how the camera is constructed itself. And we need to equalize that. So there are a couple of different ways to do that. One of which I use the most is finding a star in this star field that emits a white light. So all these bright stars are cataloged, and their color, actual color, is known. And I just need to open the catalog. Well, I do not do that myself. There is an algorithm that does that. Finds the star that's white and corrects the intensity of red, green, and blue so that the star in the image would be white as well. And that results in image looking like this. So instead of some weird yellow greenish tint, we see what's expected from the galaxy, in the blue outskirts and yellowish core. After that, we apply noise reduction, and I'm not going to show that here because it won't be visible through the stream. But after all the various tools that we use, we increase saturation, color intensity, remove gradients, etc. The end result looks like this. So basically, we start with something that looks like this. Something that looks like this, and we end up with something like this. I've shortcutted some of the parts of image processing, but main ones still are here. One main one that I omitted was that when we capture the images, they're usually not ideally aligned one to the other. So if we were to overlay one image over the other, the stars would be moved a little bit differently. For example, here, the image is turned upside down, but it's the same object, similar field of view. But we need to adjust that. So there's an algorithm that checks the stars, their location in the image, and adjusts other images according to the main one, so that they would be they would look and same, would be oriented the same way. They would be moved the same amount of space, and then we could combine them together. So yeah, that's pretty much it for me.
Thank you so much for the presentation.
I hope it wasn't too long, and it gave at least some insight into what is astrophotography. And if you have questions, please shoot away.
Sure. I'm just going to turn. Yeah. So does anyone have any questions?
Yeah, I do.
Can you see me or the screen?
We can see the screen with the photograph, so maybe you could stop sharing the screen now, and then people can.
I'm trying to find a way. Oh yeah.
There we go.
Okay.
Yeah. So, what was the question?
I don't know if you can hear.
Yeah.
Can you hear?
Yeah, I can hear.
I wanted to ask whether you could share some more photos that you have done.
Yeah, I sure can share. You can also visit my website, arturas.space, and check out them yourself on a better quality rather than streaming here. But there we go. So some of the older ones, or for example, I had this image at the end of my presentation, which was titled Ask Your Questions. This nebula is called question mark nebula.
You had one more question? No? I wanted to ask whether you've done any daylight astrophotography, if it's possible to have the results.
I rarely do any daylight photography. I tried some. It's not really for me. Main reason is that daylight photography is more about art. And astrophotography, why it appeals so much to me is because it's more technical work rather than art, from my perspective. And I'm a person that, well, I'm a developer, so that means I like technical stuff and mathematics and algorithms of all this. So this part that it's really technical is what's appealing me the most.
Does it mean that the photographer reflects the reality in the space?
I'm sorry, I didn't hear that.
Does the photography reflects the reality in space? Or is
Oh, okay. Yeah. In general, yes. Now there are a couple of caveats. So in my images, galaxies, for example, they do reflect the actual reality and the actual colors, how they look like. So for example, Andromeda Galaxy here, it has bluish outline, so that means it's young stars, new stars are being created, and the core of the galaxy is more yellow orange, so the stars are older there. Now the different thing from actual reality is that I have these pink regions that are well, they are there, but they are not that intense. I had imaged it through the narrowband filters, so I could increase the intensity of star-forming regions inside the galaxy. So it's not exactly one-to-one natural view, it's enhanced view. But everything there exists. Now, with the nebula, it's a bit different story. Everything here exists, but the colors might be completely unnatural. For example, here in these images where you can see dust, the color is real. The brown, the blue of the stars, these colors are real. They are completely natural. And then we have narrowband images like this one. And the colors here are not real. Well, the real colors of this image would be basically everything would be this red, pink, purple-ish color. And that means that you wouldn't see that so many details and so many differences. Yeah, I have the natural color of that region of the sky, so you can see the purple, the red, but the details are not that clear, and differences between parts of that nebula are hidden. What narrowband imaging allows me to do is isolate specific light spectrum, for example, that is being emitted by hydrogen or doubly ionized oxygen or sulfur, and then use those details to showcase how different that nebula consists of such different elements. And the way to showcase that is to assign arbitrary values to colors of those images. So I have hydrogen alpha, oxygen, and sulfur. And then I just say, okay, sulfur will be red, hydrogen will be green, but in reality, hydrogen is red. And while processing, I assign that hydrogen will be green, and then oxygen will be blue. And well, in reality, oxygen is this green bluish kind of electric color, and that results in an image like this. So colors here are completely unrealistic, but it allows to differentiate between different elements much better, and the contrast inside the image is much better. And it's this combination where I assign hydrogen to green and etc. is not something that I came up with. It's this kind of combination was invented by NASA when processing data from Hubble Space Telescope. So I use known ways to present the data of nebula, but it's the colors are not realistic.
I have a question. How you choose like what you take picture of? Is it like scientific, like you just collect like galaxies one after another, or is it like how you choose that today I'm going to picture this particular galaxy, or is it like visual interest? This is more spectacular than another one. Like how you divide it, how you choose it, what you're going to picture.
Yeah, so I mentioned it a little bit earlier that there are a couple of limitations when choosing a target. So first is the season of the year. For example, certain objects do not rise in the night sky at all because they are hidden behind the sun. So the Earth has to rotate around the sun a certain amount so that those targets would start rising in the night. So usually that's galaxies. And then it's basically based on mood, or maybe I find some obscure target that's very interesting and rarely imaged. So, for example, this Starburst Galaxy. It's a rare target. It's a tiny galaxy. Not many people image it, but I saw it one day and I thought, okay, this looks cool. I want to image that. I want to see how many details I can reveal in it. And it just then I just started imaging it. It was right time of the year, basically it. And then there are other targets like Andromeda Galaxy. It's a very popular target. It's very bright in the sky. It's a very big one. It's like 4 times the diameter, 4 or 5 times the diameter of the moon. Like if you would put the moon at the same scale here, it would take 5 moons to cover the diameter of the galaxy visually. But it's a cool target. It's easy to image, and then sometimes just want something simple. So there is not too many rules in picking the target. In the end, it boils down to mood, basically, I think, and the time of the year.
What was so special about your photography that NASA selected it?
I don't know. In the end, you'd have to ask them. But the process of being selected for NASA astrophotography of the day is that you submit them images, and they pick out one image from many thousands of images that they get sent. I've started sending my images probably in 2016, and something clicked with that image. Maybe one of the reasons. Well, I'll open that image. It's that image that was picked is called a hidden galaxy. So why is it called a hidden galaxy? Here we go. This galaxy is located behind one of our own galaxy, our Milky Way galaxy spiral arms. So our own galaxy is hiding the light of this galaxy, and it's making it dimmer than it should be. If there were not our own galaxy in the way, that galaxy would shine almost as bright as Andromeda Galaxy, and we could even see it with the naked eye. What's so different with my image? I've tried processing it in such a way that it would seem that it's not hidden. In other people's images, you can clearly see that it's behind this haze, which is created by our own galaxy. And then I tried to remove it and make it so it would pop out of the background, and it would be really bright and shine. So maybe that's the reason why they picked it. I don't know.
I have a question. When you take a picture of like each galaxy, for example, every year, do you actually see the difference? Can you actually see through the telescope something moving and changing?
With the galaxies, no, you cannot see changes night to night, or even a couple of years between the shots. They're just too far away and too grand to change so fast. But that doesn't mean that space is static and that there are not targets that do not change. But it's usually not galaxies. It's usually objects that are in our own galaxy. So some nebula, oh, okay, I'm lying. One thing is possible to see. It's supernova explosions. You can see those from the other galaxies. So yeah, you could see the change, that one night you image the galaxy and then the other, and you see one new star in that image of the different night. And that means that a star exploded in that galaxy, and it's so bright that it appears as a separate star. So yeah, okay, that one is true. But with the nebula, there are a couple of nebulas that are even called variable nebulas. So they change rapidly. Some even change week by week. And you can see some gases being emitted and changing or rotating inside the nebula. For example, there is a Hubble Variable Nebula. I haven't imaged that one. There's Crab Nebula. That's a star that exploded around 1,000 years ago. It was visible naked eye when it exploded in Earth. There are many writings in history about it. And currently you can see the changes inside that nebula, how it's expanding, how the how the dead star is spinning around it, and it's creating this vortex of matter around it. And there are people who are making images like 10-year in 10-year interval, like making one image per year and seeing how it's changing over 10 years course. So yeah, that there are some things you can see that are changing in space.
Another question was when you showed how you set up to take a picture that for a sequence of 255, I think it takes 5 hours to make the sequence of picture. Does it mean that if the night is longer, that you can make a better quality of picture, or does it only mean that it's more pictures? And does it depend on the way where you are on the globe that the quality of picture you take off? If it's more to the
Okay. Yeah. So it depends on target. If it's risen, so depends how high it rises during the night. So if I start imaging at 8 p.m. and it's already high enough, I can start imaging it. But if it goes down at 12 p.m., then that's it. I cannot image it further. If it stays up till 6 a.m. and it's still dark at 6 a.m., I can image it 8 hours, no problem. The longer I image the same target, the better quality, the better details, the more details I can reveal in the image. This is the reason why I keep imaging the same object a few nights in a row. If the target just sets down earlier or rises only late in the night, I cannot take enough pictures, so I need to do a couple of nights so I'd gather enough data.
Do you personally believe on life on another galaxy? So have you ever seen any weird activity that you cannot explain, like what's happening there? Yeah.
I have never seen any, but I do believe that there is life in other planets. That's like for sure. Is it intelligent? I don't know. Maybe some. It's a very interesting and philosophical question. I'd like to see some hard proof that life in other planets exists in my lifetime. I hope that we'll see some, but for sure it's impossible that it would not exist. Just.
I have two questions.
Okay.
What did come first, photography or astrology?
Could you repeat that?
Like you got interested in the photography first, and then in the theme afterwards. What came first?
I've started this hobby with just visual observation, so just astronomy and looking at the objects in the sky. And only after that I started astrophotography.
Because it's asking a lot of knowledge in both fields, so it's interesting how much do you.
Well, yeah. I'd put myself first as astrophotographer, second as an amateur astronomer. I know more about astrophotography rather than astronomy itself.
And what's more important for you personally, like the beauty that you capture or the information that you can give to others?
Well, first and foremost, my priority is to capture data for beautiful images, and then I can, if I'm already, well, for example, I have two pieces of equipment, and if I can use one for capturing beautiful images, then I can, with a free, lightweight heart, to go outside and to do some, let's call, playing science. So, for example, capturing some, for me, not that important things like comets or exoplanet transits. So I've done some experiments this autumn trying to capture the transits of planets around different other stars. So when the planet goes in front of the star is dimmed by that planet. So if you're comparing the intensity of light of that star, you can see there's a dip where that planet crossed the star in front of that star. So that kind of stuff is astronomy. It's citizen science. It's interesting, but for me personally, priority number one is my images.
Is that it? No more questions? No?
Lot of inspiration.
Yes.
Thank you.
Thank you.
Thank you
All
so
right, cool. Thank you.
quite sad that you were not able to arrive, but thank you so much for doing this online presentation and enlightening us about all the technical things that goes behind taking these beautiful photographs.
Okay, I was glad to. Yeah, it's shame I couldn't come. I just got a little bit sick
Okay.
a few days ago. So
Health comes first these days.
yeah,
Okay, thank you so much.
right. Thank you. Bye.
Okay.
Is he your friend?